So welcome you all to Hope Church Adult Ed. People are still pouring in, but I don't want to steal minutes from our guest, Tim Pennings. Tim grew up. Tim grew up in rural Minnesota. He attended the University of North Dakota as an undergraduate, and where he took a master's degree in mathematics and physics. Then did a mathematics PhD at Iowa State University, from which he came to Hope College, where he was in the math department as my colleague for 16 years. Then he was, for a time, he taught at and chaired the math department at Davenport University. Now he's teaching courses for Calvin University. He just can't give up and stop teaching because he loves math teaching. He loves teaching children and adults concepts of math and helping them understand why math is fun. And that's the experience he's going to give us here in the next couple of weeks. He's also famous for his late dog, Elvis, who's even more famous than Tim, I think, who turned out to have an intuitive knowledge of calculus displayed as he would retrieve objects that Tim would throw. And that led to Tim's writing about his dog's intuitive calculus and giving like 200 presentations at various schools and conferences and so forth. Tim has one of the most insatiably curious, questioning minds I know. I've been in his seminar classes. I've seen him questioning me and others. And he manages to challenge and question whoever he's talking to. If he's talking to conservatives, you'd think he's on the left end of things. If he's talking to progressives, you'd think he's a conservative. And that questioning mind has influenced his own religious pilgrimage. There's a lot of people that describe themselves these days as spiritual but not religious. Tim is the rare bird who describes himself as religious but not spiritual. He loves being part of the Hope Church community of faith and experiencing transcendent worship, singing in our choir, and being one of us, loved by us and loving us. But he's not sure about the God business. And he's joined by some others that maybe have their doubts as well. And yet, if you think he's not biblically literate, Tim Pennings, during his undergraduate and into his graduate days, spent 6 years active with Campus Crusade and in a leadership role. He could tell you the 4 spiritual laws. His Bible was annotated cover to cover, more than yours or mine ever has been. He's probably the most biblically literate person in this room. He was a member of the Evangelical Free Church. He went through the catechism. He knows all that stuff. He spent 15 to 20 hours a week doing Bible study. And yet he loves to ask today big, probing questions about the nature of life, the nature of the universe. He's funny, but he's also a very kind person. And if you talk to Gordon and Jill, I suspect that they would tell you there's no person in the Hope Church congregation who pushes them more, but who also affirms and compliments and appreciates them more. Because I'm copied on some of the emails that go to them. And so this is this dear friend of mine, this sparkling personality, who, as you can see from his title, asks a provocative question. Immediately I said, mathematics versus truth, not truth via mathematics. Given that choice, I think I would choose truth, not math. And Tim said he would too, but he'll have to explain that to us now. Tim Pennings.
Okay, thank you, Dave. I will pass out little sentences to anyone who came late as I talk here. And look at just your own, no one else's.
Thanks, Tim.
Uh-huh. There you are, okay. Yeah, Dave's a good friend. As he said, I copy him on a lot of the things that I otherwise just send some old friends and relatives, not that he's not an old friend.
You can pass them out.
Oh, thanks. And what's cool is, being a psychologist, he realizes the power of intermittent reinforcement. If you get reinforced every time and you stop, then the behavior dies out. But he will send me a reply, just, every occasional one, which is enough to kind of keep me always putting him in the string. So pretty clever use of his knowledge there, either deliberate or not. As I was thinking about this talk this morning, I've given this talk many times, but I'm just a little, I shouldn't say nervous, but more excited than usual, just because I realize what a great class this is. I sit in it whenever I can. I'm usually in choir, but sometimes I have to come here for the first 10 minutes and then I have to pull out to be in choir. Pulling out of this group is kind of like when I'm listening to NPR going to the grocery store and I just can't get out of the car because there's something on, and maybe some of you have experienced that. And so there's a lot of great stuff going on here. And then the very last thing I'll say before I get into it is glad to see y'all here. As Monty Python used to say, this is be ready for what? Something completely different, right? Something that doesn't necessarily have a strong application to it. It's not like you go out and change the world after hearing this talk, whatever. I actually developed these, maybe somewhat ironically, when I was, Jane, you get one of these for sure.
Oh, yeah. I got one right under my arm.
You do? Oh, okay, you're good. When I was at Davenport University, after 25 years at Hope, being part of the liberal arts there and just loving the liberal arts, I went to Davenport for 10 years. And they were very different. The pre-college conferences that we had generally dealt with things like how to run a flipped classroom and how to use technology. And that's, and I thought, oh man, I'm so tired of that stuff. And so I developed these talks just to introduce some pure liberal arts. This is to the faculty and staff there, and actually combined a couple of them together to form this talk now. So the point is, it's written for a general audience, and hopefully you'll find it totally accessible. You got one, okay. So let's begin. You'll see where this ties in here pretty quickly by go ahead and reading your sentence. Don't look at anyone else's. Just read your own particular sentence. Yeah, don't read anyone else's. The hardest part of this is to keep people from talking. I see the Leidens are already sharing theirs. See, it's just people are just sinfulness is in our. It's all part of the original of the fall. All part of the fall. So just read your own, and now after reading it, just something simple. Just count the number of F's. Count the number of F's in your particular sentence. All these married couples are all helping each other. It's real interesting. Okay, good. Okay, very simple. It's no trick to it at all. Just count the number of F's in your particular sentence. Okay, so I'm trying to remember how many of each I gave out, but anyone who has a sentence with 3 F's, with exactly 3, raise your hand. Okay, you can look around the room. Kind of look around, see how many had that sentence or those sentences. Okay, put your hands down. With 4, okay, a couple like that. With 5, okay, a couple there, and some with 6, I think. Okay, there are a couple with 6. Okay, now I have a pretty good idea of how many of each one I passed out. So I think some of you may be wrong. So count again, just to be sure, okay? If you don't want to be one of the wrong ones. You're among people here that you've known a long time. No one wants to be embarrassed on something as simple as counting the number of F's. No, don't say anything now. Okay, you got to keep quiet if you see anything more. Okay. Count the number of F's. Okay. Okay, let's count again. This is simple enough. Okay, you've had your coffee. How many with 3 F's? Raise your hand. Okay, look around. Looks like about half. With 4, with 5, and with 6. Okay, a few more. Okay, so now don't say anything. Again, man, this is tough. Okay, you all have the same sentence. Don't say anything. Don't say anything. You all have the same sentence. All of you, believe it or not, don't say anything yet, have 6 F's. Just ponder that for a moment. I've won a lot of Snickers bars with this. How many are confident that I'm wrong, that they have 1 with 3, for example? Anyone? Okay, some of you are very confident. Okay, now it's for lack of time, I'd love to milk this as long as I could. But everyone else, or not everyone, but those who found 6, what are the 3 that they're missing? Of, and of. Isn't that interesting? Isn't that interesting? I understand. Bob, did you get it this time?
I knew ahead of time.
Okay, very good. Yeah, you
Failed 4 times.
4 times. There you go. Okay. So he's been in on this talk several times already. So I understand that it's not just because it's a small word and not just because it's even at the end of the word, but it's because unconsciously you are counting the number of times you make the sound, even in your mind, finished files. And if you notice when I said count the number of F's. I even kind of accented that, okay? So you were set up to fail, something that every teacher enjoys having that ability. And so there you are. Okay, so that's going to come into play here in a little bit. So hold on to that thought. So here we go. Battle of the Titans, mathematics versus truth. And so Euclid to Einstein, how eggheads changed history. So Euclid, back about 300 BC, was the first person to ask a very modern question. He said, how do we know? He applied it just to geometry. How do we know that these 470 theorems of geometry that all of us learned roughly in the 10th grade are actually true? You know, they had been used already for thousands of years, presumably. There's Euclid. Rules such as, you might remember, the interior angles of parallel lines add up to 180 degrees. These kinds of rules had been used, obviously, to build chairs, to build houses, to build the Greek and Roman architecture, to build the pyramids of Egypt, okay, let alone everything else. So they had been successfully used all this while. No one ever doubted that they were true. So it was kind of a unique, insightful question of Euclid to ask this question, how do we know? Going back to what Dave said to me, it's this kind of this natural skeptic. Just because it's been true, just because people use them, how do we know that it's true? So what Euclid did is he took these 470 assumed facts of geometry that had been used, and he rearranged them and studied them and saw how they were dependent upon each other, and he realized that you only needed to assume a priori, that means without any evidence, without any background, to assume that 5 of them are true. And given those 5 as a foundation, as a basis, you could then use just the rules of mathematics, such as equals added to equals give you equals, just kind of common sense rules of math. You could get the other 465. Again, things that you probably did back in the 10th grade if you had the same curriculum that I did, okay? So those followed from the first 5. So here were the 5. These were the foundational ones, okay? 2 points determine a unique line. So if you have 2 points on the board here, there is exactly 1 line, which is the shortest distance between those 2 points, which connects those 2 points. Not more than 1, exactly 1, okay? How obvious is that? Secondly, once you have that line, there's only a unique way, there is only one way in which it can be extended. It can't go up this way and go down this way. It's going to go only in one direction here and in one direction there. Again, how obvious is that? Then circles. If you have a point right here and you give me a certain distance, which I'll use as the radius, then there's exactly 1 circle which has this point as a center and which has that as the radius and which forms a unique circle. Again, no one's going to quarrel with that. All right angles are equal. I haven't had actually a geometry course since the 10th grade myself, so I'm not even sure why this one is needed. It just seems so obvious, but apparently that's needed as well. It's certainly obvious. And then here's the last one. Given a line, so here's a line right here, and a point not on this line, like right there, there's exactly one line, uniquely, one line that goes through this point and which will never intersect this line, okay? So they're said to be, what's the word? Parallel to each other, okay? So that's the fifth one. Now already, if you notice these five, do you notice, don't think too hard on this, do you notice a difference between the fifth one and the first four? Yeah, look, it's 4 times as long just to even state it, right? Okay? Plus, it talks about things going on, forever and ever, and it's not the type of thing you can necessarily just put on a blackboard or a whiteboard. So mathematicians, they for thousands of years actually, they didn't disagree with the fact that this was true. They didn't doubt that this was true, but they didn't feel quite right letting this be one of the axioms. They would really much rather just have the axioms be the first 4 and then prove this thing along with the other 465 from those 4. Does that make sense? So no one doubted that it was true, but they just didn't want it to be one of the foundational things because it just wasn't quite as obvious as those. Okay, everyone with me? Okay, so through the centuries, geometry as a whole was held up as a supreme example of truth. Why? Its foundation was on these 5 foundational facts. The other 465 followed from these through logical deduction. And finally, the proof was in the pudding, right? It worked. Everything, all the pyramids they made stood up. All the things they built all worked. It all worked. So there was nothing at all to give them any reason to doubt it, okay? So, just as the philosopher Immanuel Kant was claiming that geometry was the prime example of truth, okay, and he used that as an example when he had his theory of philosophy, a little cloud appeared on the horizon. And I always like giving this story. As Dave said, my father was a minister, and he loved the Bible and studying it, and he used this book by InterVarsity Press called Search the Scriptures. It was a 3-year Bible study course that took you in a systematic way in 3 years' time through the entire Bible, asking questions, and then you could write your own answers, and by the time you're done, you have your own commentary. And I started that as a sophomore in college, and for the next 3 years, I didn't skip a day. If I knew I was going to be traveling or something, I'd work ahead, and so I stopped three years to the day from when I started, and I got a bunch of friends of mine that started as well, and so we'd get up at 7 or 6:30 in the morning and have a little quiet time, and we'd work through this. So maybe through that, or I can't remember where I first heard this story, but there's the story of Elijah, who, how does it go? He had told King Ahab and Jezebel that because of their wickedness, it wasn't going to rain. Then he ran off into the desert to live by himself for 3 years. It didn't rain, and this is when a little voice comes to Elijah, which is one of those wonderful verses of the Bible. There was no whirlwind. It was just this still small voice. And anyway, told Elijah to go ahead and do battle with the Baal prophets and Ahab. So he gathered all these prophets together. They got on Mount Carmel. What did he do? He told the prophets of Baal, go ahead and build yourself an altar and put the sacrifice on it. And then instead of you lighting it, you ask your gods to light it for you. Let's see if these gods are really there. Do you know this story? And so, of course, they pray and they cut themselves with knives and they plead and they dance and everything else, and of course, nothing happens. Then Elijah takes his and puts the sacrifice on it, and just to show there are no tricks, he dounces it with, I think it's 7, it's always 7 in the Bible, 7 pails of water, gets it all nice and soaking wet, fills up a trench around it with water, and then says, oh God, show them that thou art the true God, and then the fire comes down from heaven, very much like the scene from Raiders of the Lost Ark, right, where it comes down and blows everything up. And then, after it hasn't rained for 3 years, Elijah asks his servant, he says, okay, I've prayed for rain now. Go and see if there is something, indication of rain on the horizon. He goes, comes back, nope. I think it's again 7 times. Is that right, Don? I think it's 7 times, back and forth. The very last time, he says, there's a little cloud, no larger than a man's hand. Elijah says, get the heck off this mountain. And he goes running down the mountain faster than he outruns the chariot horses, and of course the rain comes. So that's a wonderful image, right? Something that seems very innocuous, okay? No threat at all, but aha, something new was coming, something was changing. So anyway, there's your Bible story for the day. So what was that? Well, we've already talked about it a little bit. As I say, mathematicians didn't like that 5th axiom, and we already talked about why, okay? So they tried to prove it from the other ones, okay? So this is what they tried to do for centuries, okay? Try to prove it from those first 4. And one of the ways you prove things in mathematics is it's called a proof by contradiction. You assume it's false, and then if it is false, then you get some contradictions that come that obviously aren't true, and so you say, well, it can't be false then, because if it's false, all these other crazy things happen, so in fact, it's got to be true. And that's what they tried to do, and some who tried it, they came up with some kind of crazy contradictions. They said, okay, if that 5th axiom isn't true, then in fact, if you take the sum of the angles of a triangle, anyone remember this from your high school? If you take the interior angles of a triangle, that adds up to how many degrees? 180, okay? And it turns out that if you don't assume the 5th axiom, then you get that this adds up to greater than 180. So for a while, mathematicians said, okay, there's our proof. There's our proof. That's obviously false. And so it must be that 5th axiom, you can't assume it's false after all, you have to assume it's true. Okay? Then Gauss came around. And he was the first one to realize that changing the axioms of geometry were like changing the rules of a board game. As long as the axioms were self-consistent, they just resulted in a different but equally good game. In other words, what Gauss realized is you take these 5 axioms and you change one of them, such as that 5th one, and you're going to get another geometry which, does it model the real world? Maybe, maybe not. It doesn't matter, but it's still self-consistent. It's just like 2 families that each play Scrabble their own way, right? And one plays it this way and one plays it this way, and as long as there are no inherent contradictions, they both get along fine. I'm a mentor for Kids Hope, and years ago there was this little 4th grade gal that I mentored, and she liked to play chess. So I would play chess with her over at Vanderbilt, and she would take her bishop and she'd go like this with it. And I'd say, no, it's got to go just diagonally. And she'd say, no, that's the way I play, is to do this. Okay, so that's fine. So then a little bit later, I did that. She said, no, you can't do that anymore, okay? I had to actually stop playing chess with her, even though I was just doing it for the fun, because it was just it was too tough for me these changing rules, okay? So dynamic rules. So anyway, that's the point, is that as long as you're consistent, you're good, and that's what he realized. And that changed the world, okay? That realization that you could have these different geometries that were equally consistent, and in that sense equally true, changed the world. Okay, so just to be clear, before that, geometry was used to show that truth existed. If you wanted to say truth exists, just like Kant, you said, look at geometry. Why? It rested on the sure axioms, even including the 5th one. It rested on sure axioms. You used deductive method of proof, logical deduction to get the rest of them. And then it was all self-consistent. There were no inherent contradictions. And then finally, once you finally got the final results, you could use it to build furniture and everything else. The real world verified it. So does truth exist? Of course. Geometry. What more can you ask? What's the definition of truth if not that? Okay? But now, since Gauss, And since these non-Euclidean geometries, we realize that Euclid's geometry is just one example of many possibilities. There are different geometries as well, and in fact, at the college level at least, students learn various geometries other than Euclid's. Just because something is self-consistent doesn't mean it's true. Just like a board game, it's self-consistent, but you wouldn't say that chess is true, you just say that it's consistent, okay? Just because something is verified by experience doesn't mean it's true. The modern philosopher of science, Karl Popper, is the one who kind of realized this. He says, in science, have you ever thought about this? In science, you never prove that anything is true, okay? Is there such a thing as gravity that pulls things to the earth? Let's check it out. Well, yeah, okay. Now, you saw it happen, but now watch this time as I let go, okay? You know what you think is going to happen. Are you ready? Watch. Oh, I did it again. Okay? Okay? So it just keeps doing it, okay? But the point is you never prove gravity by doing that. All you have to do is ever have it once stay here and you've disproved gravity, right? But as long as you've done it, you've never proved that it's there. All you've done is gotten more and more evidence that it's there. It's like taking a coin. If you take a two-headed or just a regular coin and without looking at both sides and just flip it over and over and over again, if you keep getting heads 10, 20, 30 in a row, you become more and more convinced that maybe in fact it's a two-headed coin, but you never actually prove it, right? It might be that you were just lucky or unlucky, whatever the case may be, okay? So without looking at both sides, just by flipping it over and over again, you never know. Just by doing experiments, you never know for sure. That's an important thing to understand about science. That's why science, you never prove anything true. You just get more and more confidence that it is true. There was a professor at Iowa State who was a mechanical engineer who, if someone came to him with a perpetual motion machine, he would check it out for $50. And of course, he, quote, knew as well as anyone that it's impossible. You basically are creating energy. But his whole point is, we don't know it for sure. It's just that we're pretty sure about it, but we don't know it. We can't say for certain. And so he would check it out. Okay, I think he never had to pay for it. Okay, so what the heck does truth even mean then? Okay, so here is by Morris, a mathematical philosopher of the 20th century. He said, all people prior to non-Euclidean geometry had shared the fundamental belief that humans can obtain certainties. The solid basis for this belief had been that humans had already obtained some truths, witness mathematics. No system of thought has ever been so widely and completely accepted as Euclidean geometry. Men such as Plato and Descartes were convinced that mathematical truths were innate in our minds. Kant based his entire philosophy on the existence of mathematical truths. But now, philosophy is haunted by the specter that the search for truths may indeed be the search for phantoms. The implication of non-Euclidean geometry, namely that man may obtain to acquire, that may not be able to acquire truths, affects all thought. It's like dropping a big rock in the pond and it just ripples out. Past ages may have sought absolute standards in law, ethics, government, economics, and other fields. They believed that by reasoning, one could determine the perfect state, the perfect economic system, the ideals of human behavior, and the like. The standards sought were not just the most effective ones, they were the unique, the true, the correct ones. Our own century is the first to feel the impact of non-Euclidean geometry because the theory of relativity brought it into prominence. It's very likely that the abandonment of absolutes has seeped into the mind of all intellectuals. We no longer search for the ideal political system or the ideal code of ethics, but only for the most workable, the most being pragmatic. That's Morris Klein. Josh McDowell. How many know who Josh McDowell is? Okay. I actually met the man back when I was in college, and I was active in Campus Crusade for Christ. He's been a speaker with Campus Crusade for 40 years or more. He wrote Evidence That Demands a Verdict. He came to our school at UND and talked and everything. And then I heard him again at Central Wesleyan, maybe 15 years ago. He was still in his 70s or so, still making the circuits. And he mentioned there something really interesting. He said back in the 70s, when he would give his talk about the resurrection and Jesus being the Son of God and all this, he said people would raise their hand and they'd object and they'd say, that's not true. Prove it. It's not true. I don't believe it. He said now, when he gives the same talk, people raise their hand and object, but their objection is different. They're not saying that's not true. They're saying, you're not being tolerant. You're not being tolerant. Isn't that interesting? It's a whole different way of thinking, a whole different way of thinking. And he's noticed it just over his career. So truth is not even thought about as much. And this is since the time of this quote, which is back in the 60s maybe. Okay? So let's dig into this just a little bit. How can there be different geometries from Euclid? And consider a globe. Okay? So I'm going to I brought one of my own here. It's interesting that we had trouble picturing non-Euclidean geometry when actually we live on a non-Euclidean geometry. A straight line is the shortest distance between 2 points, okay? So if I take this and just draw it tight, I've got myself a straight line between those 2 points, agreed? Same thing on a globe. A straight line is the shortest distance between 2 points. If I just take any 2 points, such as, say, Grand Rapids, Michigan, and say London, England, I'll be heading over there later on this summer, right there, and I draw it tight, okay, there it is, nice and taut. Notice that the straight line doesn't follow the latitude line, as you might first think, but it goes north and it goes close to Greenland. So if you've made that trek, you might well have been able to look down and seen Greenland under you, okay? So a straight line is just the shortest distance. So in particular, the equator is a straight line, agreed? Your longitude lines are straight lines, okay? They're nice and taut. But any latitude line other than the equator is not straight. If I just lay it across there and pull it straight, notice that it doesn't stay along the latitude line, it goes north of it in the northern hemisphere. See that? So straight lines are longitude lines, the equator, and any other line that I want to just go like that, that's a straight line. So you can play with your own globe at home, but notice that any two straight lines on a globe are going to have a point of intersection. This whole idea of being able to have a straight line and then a point not on the line with a parallel line, nope, it ain't true on a globe. Any two lines are gonna intersect. Here's your equator right there. Think of that as one of them. Any other one that I make on here, whether it be like this or like this, it's going to cross the equator. Make sense? They're always going to cross. So that's kind of interesting. So what was discovered? They discovered, what did they say? That if that fifth axiom wasn't true, then triangles would have something greater than 180 degrees. Well, let's see why that's true. Let's think of this triangle right here. Let's start at the North Pole, go all the way down until you hit the equator. Okay, now you're just going to have to visualize this, and then go along the equator and then back up again. You follow that? So these two angles right here, where it hits the equator, that's going to be 90 degrees. Right here, it's 90, I forgot my third arm here. That's going to be 90 degrees, and then I still have this angle right here. See that? So it adds up to a greater than 180 by the time you're done. Make sense? So it's just a whole different geometry, okay? And so there are no parallel lines then. There it is. Okay, so that's just what we talked about. Okay, so once we have that, then the question is, what's the shape of our universe? Okay, we know what the shape of this whiteboard is. It's Euclidean geometry. We know what the surface of our Earth is. It's spherical geometry. But what about the shape of the universe? It's, of course, in 3 dimensions rather than 2, but the same question applies. If you were to take 3 points in the universe, just way out in space, and draw lines between them, and you'd have to use like a laser beam in order to get a line, then if you were to add the sum of the angles of those 3 points, would it add up to 180 degrees or would it add up to more or less? What's the shape? And it turns out that you really can't determine it that way because you'd have to just go way too far out in order to be able to make the measurement. So scientists are still trying to get a sense of what the shape of our universe is. But in particular, if our universe is shaped like a sphere, then if you were to shoot a straight line out, that is like a laser beam out, and you just let that laser beam go far enough, then that laser beam is going to end up bending around, and you're going to end up coming right back where you began, just like what happened here on the Earth with the lines. Okay, I'm getting ahead of myself just a little bit. So here, let me give you the, yeah, okay. Oh yeah, okay, here we go. So let's talk about Einstein. Most physics experiments are done by first observing something in the real world and then coming up with a theory that makes sense of it. Einstein did something totally different. He did these mind experiments which he thought through the theory before he ever had the evidence for it. So here's what he did. Here's what he did. He said, suppose this room here is floating out in space, and there's no windows, so we can't see outside, but we're all in this room, and we're just floating out in space. Can you imagine this? And so we're just kind of floating around in it, and we're bouncing from wall to wall and kind of shaking hands as we pass people and pushing off each other, and we're just floating around. Are you all with me? And then all of a sudden, we all find ourselves pressed down to the floor, okay? We all end up down to the floor. One of two things may have happened. Either we've landed on a planet, and so that planet now has gravity, which is pulling us down. Are you with me? The other possibility is that let's say this is the room right here, is that maybe there are some jet rockets on one side of this room, on the bottom of it, that have shot off, and since they're shooting off, they're propelling us upward, or whatever, in one direction, and since we're being propelled this way, we all find ourselves being pressed towards the floor. Are you with me? Either one of those could be a possibility, okay? So hold that thought in your head. Either one of those could be a possibility. We don't know the difference. Then Einstein thought like this. He says, okay, what if there's a tiny little hole in the wall right here where a little beam of light can come through, and we see that light go across the room and hit at the exact same spot over there on that wall. Okay, we just see it. We just can kind of see the impression right there. Make sense? Suddenly, we see that beam of light, instead of hitting right there, I'll change. Instead of hitting right here, it goes and hits at a lower spot. So it bends down. Okay, it bends down instead. Einstein thought like this. He says, well, one of two things. No, he said one thing that would cause that would be if suddenly the room were being propelled upward. If the room is being propelled upward and the beam of light comes in right here and the room is being propelled upward, from our vantage point, we would see it doing what? Going down, bending down. Are you with me? So it comes in there. By the time it comes in there, it takes very little time, but still a little bit of time. And while it's traveling, the room has been pushed up, so we see it. It looks like it's bending down. Are you with me? Einstein thought like this. He says, wait a second. He said, you and I can't tell the difference. If we're in this room, we can't tell the difference between whether we're being affected by gravity or by acceleration. So it must be that that beam of light can't tell the difference either. And so since that beam of light is obviously going to be affected by the acceleration, that beam of light must also be affected by gravity. We can't tell the difference, whether it's acceleration or gravity. That beam of light shouldn't be able to tell the difference either. So he said it must be the case that light is affected by gravity, and that if you have a beam of light that passes a massive object, that beam of light is actually going to get bent by that massive object. That massive object, the gravity of it is actually going to bend light slightly. Now the problem is you need a pretty massive object to be able to bend it any appreciable amount. The only really massive object, really locally to us, is the sun, okay? So you think of the sun as being close by. So here, can you all see this? Let me turn it a little bit. Okay, get this out of the way. Okay, so here's the Earth. Here's the sun. And we need some light to come around the sun, and then we observe it at the Earth. So the only light that can come around the sun would have to come from a what? From a star. But the practical problem with seeing a star on the other side of the sun is what? The sun is way too bright. So the only answer to that is we have to wait until the light of the sun gets blocked out, which happens when? An eclipse. So back in, I think it was 1919, this is during the First World War, so people were all involved in the World War, but still, this was such an important thought discovery of Einstein's that they went around the world, and this is when an eclipse was happening, and they put these various sites around the world so that they could make sure to have one where there's no clouds. And they knew exactly where these stars were. So if the light was not bent by the sun, then the star would have to be right here before we were able to see it. But if the light was bent by the sun, even though the star were here, by the time and I'm exaggerating it, but it's going to get bent and we'd be able to see it even when it's here. Make sense? So we'd still see it. Of course, to us it would look like it's there. But we'd be able to see it earlier than expected. They did the experiment. Turned out just exactly as he said, and that's when he became famous overnight. That's when he got his fame, was with the proof of his theory of general relativity. Okay, so he basically proved that the world has this real interesting behavior where even what we think of as being a straight line gets bent, and that's why if you were to start at the Earth and you have enough mass of objects here in the universe, and you send a light beam out here, it could get bent by all that stuff and could actually come around. I remember my high school physics teacher say you'd be able to see the back of your own head. Okay, so that pretty impressive. Okay, it's easier to look in a mirror, but okay. So there you go. Okay, so recap: the discovery that there are geometries other than Euclid's has changed the way we understand, first of all, our physical world. It may be that our universe is flat, or it may be that it's curved. That's still an open question. It's affected our mental world. True is not always an appropriate adjective. It might be that consistent would be. And so there it is. Okay, so that's the first part of the talk. Then Descartes said, okay, let's do one up on Euclid. Okay, he's known for two revolutionary ideas. I think, therefore I am. He basically took Euclid's thought of how do we know that this geometry is true, and he applied it to everything we think about. How do we know that anything is true? How do we know that anything is true? And he started, just pondering it. He said, well, now, wait a second. What do I claim to be true? Well, I claim that I got up this morning, but then he thought, well, wait a second. I'm relying on my memory. And sometimes my memory falters. So I'm pretty convinced, but can I say I know for sure? Maybe not. I'm relying on my senses. But doggone it, sometimes I can't see something as simple as finding 6 F's in a sentence, right? So sometimes that falters. And so the things, if we rely on our experience or if we rely on our memory, we just can't say for sure. So then he said, okay, well, let's see now. He was thinking, and all of a sudden he thought, wait a second. I'm thinking right now. In order to be thinking, I have to exist. And so that was his beginning. That was his foundation, just like the foundation of Euclid. That was his foundational block. I think, therefore I am. And then he built it up from there. And, eventually God exists and various other things. And philosophers have found various holes in it along the way. But that was his attempt, okay? He did the same thing that Euclid did, or tried to anyway, okay? Here's the other thing that he did. It's called the Cartesian plane, named after him, Descartes. So we're going to talk about both of those. Okay, so what do I know for sure? Can I rely on my senses? Well, we just talked about that, and there, of course, you've already done that. Here's another one that I think is even more interesting. Look at those two tabletops. You've seen little things like this where you're told that, the two lines are the same size, and yeah, I can kind of see that. But this one, if I told you that this shape right here is exactly the same as this shape tabletop right there, would you believe me? I can barely believe it. So I brought this along, knowing you to be a skeptical bunch, okay? You can come up afterwards. There it is. You can just go to Google and just put in tabletop illusion, and you'll find it. But there it is, and I printed it out. There it is right there. I cut out this one, and that one lies exactly on the other one. It's totally an illusion by we're being tricked by perspective. Okay? It's just remarkable. So it's just another example that our senses can be fooled. Okay? Let's see. Is that going now? There we go. Okay? Okay, so anyway, mathematicians started wondering, how do we know that all mathematics is true? Not just geometry, but how about the rest of it? So Frege, back in the 1800s, he said, okay, let's start with something most basic in mathematics. So maybe, oh man, there's just so many fun stories here. But back in, of course, World War II, the U.S. was ahead of the Soviet Union in technology, and we built the atom bomb. And then because of the Rosenbergs, I believe, the spies, that they caught up with the U.S. pretty fast. And then U.S. built the hydrogen bomb, and they built one very quickly. And it was this technological war about who was going to kind of have the technological edge. And then what happened that shocked the socks off of us? Sputnik, right? The first, they were the ones that beat us to space. And when they beat us to space, it kind of shocked us, and we said, hey, we need to change the way we teach mathematics in particular, and so we're going to teach math starting with these basic principles like sets. You talk about a set as a collection of things, and subsets, and intersections of sets. How many have seen that before? Did you have it yourself, or maybe you had it with your kids? But yeah, I saw it for the first time in like the 7th grade. That's when they started introducing it early on. So Frege, basically, when I teach my calculus students, I say sets is a very foundational thing. Then you get functions, then you get limits, then you get the derivative, and you get all the things of calculus. But the very first things is sets. And so he started that, and so he started to build numbers and arithmetic just starting with sets. Okay? He worked for 12 years on it. Okay? He was one of the great mathematicians of his day. In 1903, just as the second volume was going to the printer, he gets a letter from, anyone recognize him? Bertrand Russell. Bertrand Russell. I've heard in 500 years, the one Englishman that will still be known as Bertrand Russell. If you go to the Hope Library or maybe the Herrick Library and find the books that it's like this. He wrote Why I'm Not a Christian. He was a famous atheist. He wrote History of the Western World, I believe, something like that. Just all sorts of things. And anyway, he wrote Frege a letter, and he said, "Now don't get in a tither on this." He says, "Buddy," he says, "I've got a question for you. You just talk about sets as if they're kind of easy to understand." He says some sets are members of themselves. The set of all ideas is itself an idea. So some sets are members of themselves. But other sets, the sets of all pieces of paper, is not itself a piece of paper. It's a collection, but it's not itself a piece of paper. So some sets are members of themselves, some not. And he said, what if you take all the sets that aren't members of themselves? Is that a member of itself or not? Okay, so don't think too hard on that. But it's similar to the barber problem. There's this small town with a barber shop, and there's a big sign in the window that says, I shave all the men in town and exactly all the men in town who don't shave themselves. Okay, he's bragging that, and this is a man himself, a barber. He says, I'm shaving exactly the men who don't shave themselves in town. And someone comes along and says, wait, that sign can't be true. Can you see why? I shave exactly the men in town who don't shave themselves. So in other words, if he doesn't shave himself, then he does, and if he does shave himself, then he doesn't. So it's got to, just like the little thing that says this sentence is false. Is it true or is it false? So you get these self-referential things. And Russell realized that sets had that same problem. And he sent a letter to Frege basically stating that. Frege writes, and he puts this at the beginning of the second volume, a scientist can hardly meet with anything more undesirable than to have the foundation give way just as the work is finished. This is 12 years. In this position, I was put by a letter from Mr. Burton Russell as the work was nearly through the press. Isn't that fascinating? Russell took no pride or joy in this at all. He wanted truth. He wanted to find truth. And so he said, okay, we have to start with logic instead. We can't start with sets, we have to start with logic. So he started with logic with the philosopher Whitehead. They spent 10 years writing, it's called Principia Mathematica, and on the page 360 of the second volume, they finally get to the point where they prove, can you see that down there? That 1 plus 1 is 2. 500 pages in, they prove that 1 plus 1 is 2. He said, here's a practical application of what we've done so far. Okay? So Russell writes this, and just note the pathos in this. He says, I wanted certainty in the kind of way in which people want religious faith. As I say, he was an atheist. I thought that certainty is more likely to be found in mathematics than elsewhere, but I discovered that many mathematical demonstrations which my teachers expected me to accept were full of fallacies, and that if certainty were indeed discoverable in mathematics, it would be in a new field of mathematics with more solid foundations than had hitherto been thought secure. But as the work proceeded, I was continually reminded of the fable about the elephant and the tortoise. Having constructed an elephant upon which the mathematical world could rest, I found the elephant tottering and proceeded to construct a tortoise to keep it from falling, but the tortoise was no more secure than the elephant, and after some 20 years of arduous toil, I came to the conclusion that there was nothing more that I could do in the way of making mathematical knowledge knowable. Okay, so practical application of this. Have you ever done this? You're in a restaurant, waiter comes, you say, the arithmetic seems correct, yet I find myself haunted by the idea that the basic axioms on which the arithmetic is based might give rise to contradictions which would then invalidate these computations. I haven't gotten out of any bills that way myself, but I'm still waiting. Okay. Gödel came along. He was a friend of Einstein's, and they were together at Princeton, and he showed that, in fact, there's always going to be some true facts in math that can't be proved, probably even more powerful and noteworthy yet than what Einstein had ever done. Let's see. I'm not going to finish what I'm doing today because I'm going to take at least a couple minutes for questions. Sorry. But are there moral truths? Consider this. 1, 2, 3, 4, 5, 6, 7. This thing right here can be written as 7 in base 10. It could be written like this in base 5. I tell you what. What do we have? Just about 5 minutes left? I tell you what. I'm gonna cut off here since I have next week anyway, and I'll finish this up and still do the other things I'm going to do. But should we take time for questions? Let's take time for questions. And then hopefully you'll be back next week if you found this somewhat interesting. Yeah.
I'm going to give the mic here, but I should just mention that the adult ed ministry team, number one, appreciates very much what you're doing, but asks that we all remember that we are now live and being recorded so that what is being said will be known by the wider world. There are a few people that have been concerned about that not being made apparent to all of us, so please be aware that what we say now is being heard by everybody else. He doesn't care, but the rest of us do.
Tim, it might be helpful to talk more about Gödel's incompleteness theorem. You mentioned Gödel, but that was a mind-boggling thing for me as a math major at Hope College years ago. And what you just described actually has been my career path. I got out of science and went into religion and philosophy precisely because of the uncertainty principle that comes with Gödel. So say a bit more about that.
So I passed by that because I could spend another hour on that. But essentially what Gödel proved is that there are always going to be true things in mathematics which cannot be proved. So here's the circle of losing my. Here's the circle of true things right here, and here's the circle of things that can be proved. The two don't coincide. So before Gödel came along, people thought that to be true and to be able to be proved were one and the same. And he showed no matter what mathematical system you ever use, this one is going to be contained in, but not complete, as the total number of true things. And so that is just another one of kind of the mind-boggling things that all kind of happened along with non-Euclidean geometries. These things kind of happened all over the span of 100 years or so, which just shook the foundations of mathematics. Is that what you're referring to? Yeah. And one nice example, Mike Gullion was someone who was actually at Hope, I think, last year, and he wrote a book years ago which had a nice example of this. He said it's kind of like a person who sees the statement using mathematics that I'll talk about this next week if you want. I'm going to get messed up if I try to do it now. Basically, trying to use mathematics to prove something, you can't do it. But then when you go home and lie in bed and just think about what you did that day, all of a sudden it comes to you, oh yeah, I was unable to do it. So it's only by jumping out of the system, not trying to work as a mathematician, but reflecting on it from the outside, that the truth of it even becomes apparent. But I'm going to mess people up more than they are.
Tim, I'm wondering about the human nature of mathematicians as they encounter new information. So you talk about Einstein's is known after the solar eclipse, and suddenly, boom, now he's famous. In my world, there's always pushback with something new, or let's look at this a different way. How was all of this new information received? I mean, because if you cannot prove these things, then why must I acknowledge that what you've developed is truer than what I hold true? That I'm going to assume I'm going to say 1 + 1 is, I'm going to say 1 + 1 is 9. How can you?
Yeah.
Not.
I don't know whether I'll answer your question, but you just prompted a couple new thoughts, so I'll answer those. My dad told me years ago, he's been dead now for 12 years, but way back, he mentioned once that maybe mathematics was the area of human endeavor least affected by the fall. Isn't that an interesting thought? Least affected by original sin. And Ken was just showing me a little cartoon quip that kind of had the same idea. But next week, one of the things we're going to touch on, I'm going to touch on several things, but one is going to be the infinite, okay? And with the infinite, there were mathematicians that dove into the infinite, proving that things were true and such, but then there were other ones that pushed back and said, no, this you can't go there. Basically, you can't go there. And Georg Cantor, a very religious man, Jewish, he ended up dying in an insane asylum, based partially on the fact that he was just getting this resistance to the new things that he was trying to put forward to the whole world about the truth of infinity. So there is a human side of it, and there is some fighting, and some people will accept it and some won't. So that's all part of mathematics, as it is everything else. So I don't know if...
The human nature, it's not a pristine...
Pride is still there. Who gets the first, who result, all that stuff is still there. So the results are pure, but who gets credit for it, whether it's important or not, those are all value judgments, and so there's all sorts of fights over that.
So Tim, your presentation is for many of us, I'm sure, set our minds to spinning. I was wondering, for example, and don't answer this question because we're out of time, but is the demise of sort of the idea of absolute truth as given us by mathematics, did that help give rise to postmodernism and the whole skepticism about the objective reality
I
of
think
truth?
that one quote, I think, said it very well, right?
Right.
That it started with non-Euclidean geometries, and that's affected
Right,
everything.
exactly,
It
exactly.
affected everything, yeah, that's right.
And then I look at Gödel's idea that the truth we can know and define is only a segment or part of the larger truth, which takes my mind to Shakespeare's Hamlet. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. And maybe that's part of what has you still here at Hope Church as a religious but not spiritual person, knowing that there's larger things than what's in your mind, and yet driven to expand that inner circle as far as you can take it.
Somewhat, it's more the organ music, though. I think.
Okay.
Is that on air? Is that on air? Okay.
Thank you. I was trying to make him spiritual. So I believe we need to set up for.
Correct. Yes, we need to. It's Pizza Sunday, so many of you know what that means, that those tables over there need to go up, and there needs to be 8 chairs around, 4 on each side. So those of you who are able, we would much appreciate it. Thank you. Tim, this was